The impact of radioisotopes in the healthcare industry has been massive. They can be radioisotopes for tracing, or they can be attached or used as labels in drugs and chemical compounds as radiopharmaceuticals. Some of the uses of radioisotopes include diagnosis of particular diseases such as cancer, treatment, so they can use radioisotopes to actually treat killing particular cells, such as in the case of cancer treatment. The sterilisation of medical equipment is another use, which is particularly important for surgeries. In the treatment of people with severe burns or with that need tissue grafts or replacement of tissues. Traditional nutritional research is another area, labelling materials that are used by the body. And another is biomedical research, and that's into things like cellular processes, what's actually happening inside cells and membranes and in the nucleus, etc. One particular isotope that we're looking at in this course is technetium-99m, or metastable. This is a very useful substance because when it decays, it produces a gamma ray. This can be then traced by the gamma camera. So where does technetium-99 come from, or how do hospitals keep it? It only has a half-life of 6 hours, which makes it good as it's an isotope in the human body. But what we're interested in is how do hospitals keep it if it only lasts for 6 hours. And here we can see how they keep it. In this equation at the top here, molybdenum is the element next to technetium, and it is bombarded in a nuclear reactor with neutrons. So we're adding neutrons. If we see here, we add 98 plus 1, we end up with 99. So we have a molybdenum substance here. It's still only 42 because there's no protons in a neutron, so it stays as 42. It does release gamma rays, so it needs to be shielded with lead to protect people operating with it. This is a part waste substance. It's called something that we use and store. It has a longer half-life at the hospital, so it is used, and it's what we call milked, or used to milk a source of our technetium-99m. And you can see in this next equation, the molybdenum decays and it produces our technetium that we're after, plus a beta particle. Okay, and now we have a source of technetium-99m. That's what we use, that the hospitals collect, and they collect it from a special machine. You can see here. And you can see there, it has a type of chromatography going on here, or filtration. The breakdown occurs up here, and the bottom part here is where the technetium-99 is collected. Always remember keep the M there, because that's the one we're dealing with. So we have our technetium. It can be used to place into the patient. It breaks down in 6 hours, as we said, and produces gamma rays, and then they're used as part of the gamma camera. And the particles in here give off our gamma rays, and those gamma rays are photographed by this machine. After this breakdown occurs, this decay, technetium-99 here is left in the body, but it produces only relatively low amounts of radiation, less than background. So this is our source of gamma rays. and we use a gamma camera to take photographs of those gamma rays. So technetium 99M, being a source of gamma rays, is used to diagnose many conditions that would otherwise need surgery. Surgery, it's invasive, it can introduce infection into the body and cause damage as it's happening. Costs for surgeries and facilities for surgery are also massive, keeping sterile conditions. And as I said, the danger of infection is very major disadvantage in the case of surgery. So technetium and other radiopharmaceuticals can be used to save a lot of money, to treat people on a larger scale. They're starting to take over in the health system, and not take over, but become very common. Other things that could be used, technetium 99M can be used to detect the skeletal system, the bone scanning, as I just said. Other things such as thallium can be used, or rubidium can be used for cardiac isotopes, to testing